Hi class. In this video we're going to look at different types of sorting algorithms, and you've seen now that you can sort data automatically using array methods and using database capabilities to order things by a certain field. So why would you need to know about sorting? Well, sometimes those sorts are not the most efficient, and if you're sorting millions of rows or millions of records, you might run into some performance problems that you might be able to take care of by implementing a more efficient algorithm. Now, when we're talking about algorithm efficiency, there's an important concept here. It's called the big O notation. And the big O notation describes the performance and complexity of an algorithm. So it kind of is a way for us to look at the process that we're implementing and consider what is the worst possible case scenario that we could encounter. Whenever we're working with data, it's important for us to think about these different data structures and different algorithms. From a science standpoint, these are the kinds of things that can be focused on in a 4-year degree or by a software project with a lot of data, because sometimes you'll be forced to consider these kinds of things. Now, as a software development professional in any manner, you need to be able to understand these basic functional patterns. So we don't want to get into thinking, oh my goodness, this is so hard. It's not. We're just talking about patterns that can be used to sort and manipulate data in a way that's most efficient. So what do we need to do? Well, we need to store data. We've seen that we need to do that in a database if we want to be able to access that data randomly. We know that we can also use many other different file formats to store data. When our data is stored, oftentimes we will also need to be able to search data to find specific occurrences. And in certain situations, it'll be helpful for us to sort the data into a specific sequence. And sometimes that's a demand of our users who need to be able to look at things in a certain order. Now, data structures and these functional patterns can help us with all of these types of tasks. Some of these data structures are suited for different functions, and some are designed for very specific purposes. But no matter what, a deeper understanding is going to give you more tools for your toolbox. So let's talk about this big O. It's the worst case scenario. Wouldn't I like to focus on the best case? Well, sure. But as a developer, I need to know what the worst possible case is that I could be creating, right? And I need to know what is the most efficient performance I could use. Now, the first big O notation denotes a constant runtime, and a constant runtime is O to 1. And that just means I'm going to do a single comparison in my program. So it doesn't matter how many data elements or rows or anything I'm looking at, I'm only going to do one comparison. This is going to give me a constant runtime, and it's the most simple. Now, a more realistic option is O on the order of n, or order n, where n is the number of elements that we're processing, either in an array or in a database or whatever case our data may be. So whenever we're looking at an array and say we want to do some sort of sort, we could maybe implement an algorithm where we compare the first element in an array to every other element in the array. This would give us n minus 1 comparisons. So with n being the size of our array, as n increases or grows larger, it is said to dominate, and it will have an impact upon performance. So the resources required on a linear runtime are in direct proportion to n. How big is n? Now, a quadratic runtime is an algorithm that compares every element to every other element. So in this case, we could have n to the power of 2 divided by 2 minus n divided by 2 comparisons. So it goes exponentially. As we add more elements to our array or to our comparison, we are increasing the resource requirements. Every doubling of the occurrence of n causes a quadratic increase in resource requirements. This is a quadratic runtime, and it's considered O on the order of n squared, or order n squared. Now there's a website, this PowerPoint is available to you, that talks a lot more about big O notation. You just need to be thinking about performance implications. So first, searching. We can have a standard search, and you guys have implemented a standard search. And here's an animation. Whenever we're working on a linear search, we're just looking for a specific item in an array. A linear search is effective on a sorted or an unsorted array, and we're going to search every element in the array sequentially from the beginning to the end and compare each element to our search element to see if it matches. Now, this is a text animation that's available. Or it was. Let's try that again. I'm going to copy this URL. Let me see what you got. Go back. Hang on, I will be right back. Okay, something seems to have happened to that animation. I found one that's working. Let's take a look at this. In this example, we have this array down here, and the items in blue are the index values, and the items in black are the values contained within the array. So if we're searching for something in the array, we're searching for one of the values. Let's try one. I want to search for, let's try 322. And I want to do a linear search. So the first thing is my logic is going to start at the beginning and look at each element in the array and see if it finds what I'm looking for. In this case, it did find it at position 9. So notice this is the way this linear search is set up. It's going to stop as soon as the element is found. Now, a linear search is very inefficient because we are looking at every element in the array. A binary search, on the other hand, splits the array into two pieces, rather like a type of sort we'll look at soon. In the binary search, you can think about The Price is Right. And if you've ever watched the game, the higher or lower game on The Price is Right, you know that a person is given a range, say that this price is between $100 and $600. Well, the really smart contestant will start at $400 or $350. And then Drew will say higher, and they'll know, oh, let's see, I want to split the difference between $350 and $600. So how about $550? And he'll say higher, and they'll go $650, and he'll say lower, and they'll go $600. And they keep splitting that difference. And that way they can figure out what the price of the item is very quickly with a few number of guesses. This is an implementation of a binary search. And in a binary search, we do just that. We split the array into two halves, and then we decide which half we need to look at. Let's look at an example here in the same place. Now, when we're working with a binary search, our data has to be sorted in our array. So let's try this as a binary search. Now, what we see here is that as we go, we're splitting out the different areas of the array. Let's run that again. So first, there's the first half is the number I want within that range. It is. Split that into half, and now see where that number is. So quick animation. I wish my Armstrong guy had not gotten rejobbed or whatever that is. Okay, so sorting. We do a lot of searching. We know right away that a binary search is more efficient than a linear search. So how do we get that data into that sorted order that we need to do that binary search? We don't want to spend so much time sorting that we override any of the performance gains involved in using a binary search. There's lots of other reasons to sort though. So the first type of sort we're going to look at is called a selection sort. A selection sort, we basically are searching the entire array to find the smallest value and moving it to the first position in an array. Let's take a look at this awesome video.
In this lesson we are going to show how the sorting algorithm selection sort works. Its function is to find inside the data structure the minimum element, and when it is found, it will be moved in the first position. Repeat this procedure for the remaining elements, not including the element firstly sorted. The maximum number of comparisons of this algorithm is by multiplying n for n-1 divided by 2, where n is the number of the elements. And now we are going to see how the algorithm works with a 3D animation.
So every time he starts, he's walking that whole remaining part of that array, looking for a new minimum. Notice in this example, he's found a minimum, but of course he doesn't know that yet. Sorry for watching a video on a video, but these are just so awesome. Now we're going to let him finish, because as he walks through this array, you'll see that it's extremely monotonous and very, very poor performing, right? You wouldn't want to do this. Okay, so here we go. Now, again, he doesn't know he's got the smallest. And again, we're in order now, but of course that's not possible to be known by the processor. So each of these last remaining numbers is going to be checked. And finally we finish with that selection sort. Did a lot of comparisons, right? Considering how much data was involved there. So super inefficient, but that's the way that a lot of internal sorts are handled if we don't take over. All right, an insertion sort is just like a selection sort. They're very similar, except this one compares each element to the prior element and swaps them if necessary. So let's take a quick gander here at this video. So each element we start at, in this case the fourth element, compares itself to the prior. Do I need to swap places with you? Oh, I do. Okay, let's swap. Then, do I need to swap places with you? No. Okay. Next element. Do I need to swap places with you? Yes. Do I need to swap places with you? Yes. Do I need to swap places with you? Yes. about you. Oh, nope, we're finding an order. Okay, now we go on to the next item. Do I need to swap? Yes. I'll let these beautiful dancers explain it. And then when we were all in order, we didn't have to make those multiple passes across the array. So it'll be a little more efficient here. So yay, we can celebrate with some Romanian dancing. So partnered up. Okay. So that's the insertion sort. It is quadratic, meaning that as we add new elements to the array, we can have a quadratic impact on performance. But the merge sort. Merge sort is more efficient, but it's a little more complex. In a merge sort, we take our binary search algorithm idea and split the array into two arrays of equal size. Then we sort each array and merge them back together. With a merge sort, we're normally doing recursive calls. Let's take a look at this awesome one. I love these 3D guys.
In this lesson, we are going to show how the sorting algorithm merge sort works. Its function is to divide the elements in the data structure into smaller partitions and sort them. Finally, must we merge the small partitions to make the original set with sorted elements. This strategy is called divide and conquer.
So now he's got his first path in order, right? Go for the second half. Now in our merge, turn that down a little bit. You're getting like a double whammy, sorry. Okay, I hope that audio didn't kill you too bad. I know it's unusual to watch videos within a video, but I really like these sort videos because they make everything so visual and we can kind of see what's happening. so much easier than looking at the code, even though looking at the code is great too. But with the merge sort, we go back to a linear runtime model, right, with big O. It's not quadratic anymore because we're minimizing the comparisons that we make by splitting things up into multiple sets. Now, whenever we are working on things with sorts, one of the sorts that you're going to implement is called a bubble sort, and I'll let you do some research on that and see how it's supposed to work. But let's look at this last video that's very cool. And we won't try to kill you with it as much.